All right, so in addition to side, 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 and side, angle, side, we're going to add on to that angle, side, angle, 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 side, and a last one, hypotenuse leg. So objectives for today, first thing, we're going to have this new thing called an included side. It's a pretty simple idea, but it's an important thing to for us when we're doing angle, side, angle, and angle, angle, side proofs. Second one, we're going to determine if angle, side, angle, and also angle, angle, side can be used to prove two triangles are congruent. We're going to write a few proofs, either using angle, side, angle, 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 side. I don't think we're going to get all the way to hypotenuse leg today. We'll probably have to finish that up tomorrow. And Mr. Bechtel added a bunch of his little jokes here, so take those as you will. All right. So this is expanding the things that we've already talked about with proving triangles congruent, just to add a few more things that we can do. So the included side. So the included side is when we have a side that is in between two angles. It's that simple. So we already had something called the included angle. So the included angle was in between the two sides. So in this case, this here was our included angle because it was in between the two sides. This one is our included side. It's in between the two angles. So that's simple, pretty easy. We're going to be making use of that. We're going to be calling some sides included sides. It's necessary when we're talking about both angle, side, angle, and angle, angle, side triangle congruence. All right. Oh yeah, and another joke, included side, the side between the two antlers. Anyway, so angle, angle, side congruence postulate, we're going to shorten that to just ASA. So if two angles and the included side of one triangle are congruent to two angles and the included side of another triangle, so we can see this here, angle A and C are congruent to angles D and F, and then the included side, the side that's in between those two angles, and the side that's between these two angles are congruent. These are the conditions for us to use angle, side, angle, triangle congruence. We have the angle, the other angle, and the side in between. We have the angle, the other angle, side in between. That's angle, side, angle. Therefore, we can say these two triangles are congruent to each other. This one is a postulate. So just like side, 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 and side, angle, side, this one's a postulate. We're just going to accept it to be true without proof. Let's look at some pictures and see if we can decide whether we can apply angle, side, angle or not. All right. First one, number one. What do you guys think? Yes or no? Put it in the chat. Can we use angle, side, angle here? Seeing a lot of yeses. I know it popped up yes already, but that's okay. Well, it's easy enough to see that we have an angle, pair of congruent angles. Right here, we have our other pair of congruent angles. If this is a right angle, this would be a right angle. And they have a shared side. So that is two angles, side in between, two angles, side in between. First one is a yes. What do you guys think for number 2? Can we use angle, side, angle or not? This one's a tricky one. Seeing some hesitant no's. The answer here is no, though it's not as clear as it may seem. We don't know a lot. We know that we have a shared side. So slanted is not too much of a problem. That's not really a big deal. These two triangles could be congruent to each other. Don't you agree? We don't know whether they're congruent, but they could be. The big deal with this one is we have some parallel sides and a transversal. So this is something that we're going to be doing today a little bit. anytime we have some parallel sides, like this right here. Oops, I didn't mean to do that. KL is parallel to NM. We can create alternate interior angles. So these angles right here and here are considered alternate interior angles because they are formed by some parallel lines and a transversal. So we know we have one set of congruent angles. We also know we have our shared side, but that's only AS. We don't have the third piece. We don't have another angle pair, or we don't have another side pair. So we don't know enough to go with this one. But we did know a little bit more than was necessarily obvious right away, because whenever we have parallel sides here in a figure, it's important for us to take a look and see if we have alternate interior angles. That's going to be something that a few of our proofs today deal with, is making sure we can make use of alternate interior angles. All right, and the last one, number 3, what do you guys think? This one's a weird one. The answer is obviously no. You guys are right on top of it. In this case, we have an angle, we have a side, and we have a side. That's the angle's not, the angle would need to be in between for us to use SAS. This is not one of our shortcuts that we know. So this one is also a no. Yeah, we obviously can't use angle side. And angle side is not a shortcut, so we don't use that one. Oh, Mr. Bechtel. Okay. Anyway, let's go ahead and clear this off. So angle side was, or sorry, angle side angle was our first shortcut for today. Our second one that we're going to talk about is angle side. And this one is a theorem. The reason this one is a theorem is because it actually is equal to angle side angle. If we know that angle side angle is true, angle side will be true. We'll look at an explanation in form of a proof of why that's the case, but these two things are actually equivalent to each other. We'll just use whichever one's easier to apply based on a given problem. So looking here, angle side triangle congruence is if two angles and a non-included side. So the non-included side means the side that's not in between. So here, notice that HJ is not in between the two angles that we're doing. And LM is not in between. That's what we mean by non-included. The other important part about it being non-included is it does also have to correspond. It has to be in the same position. So it's non-included and it has to correspond. So you'll notice that it's next to the double marked angle in both of these cases. So it does correspond. So if those are congruent in one triangle and incongruent to the other triangle, then we'll say the triangles are congruent. This is AAS, triangle congruence. Again, this one is equivalent to angle side angle, and we'll kind of show, I'll show a proof of what that means. Before we do that, there's an important theorem that we learned about briefly in 4.1 or 4.2 maybe. If you have two triangles and you know that they have two angles that are congruent, so say this angle is congruent and this angle is congruent, and then this one and this one, there's a theorem called the third angle theorem. Third angle theorem that says if you have two triangles and two of the angles are congruent, the third ones will also be congruent. So these angles here will also be congruent to each other. We need to make use of that in what we do next. So I just wanted to kind of mention it. All right, let's look at how angle side and angle side angle are actually the same thing. So this is a proof of the angle side congruence theorem. So we are given angle side, and we're trying to prove that means we can also use angle side angle. It's kind of a tricky little proof. It's really short, but here we go. So our givens are, we have two congruent angles, so angle G and K and angle J and M. So we have our two angles, and we're given the non-included sides. So we're given AAS. Hopefully you can see that. It's two angles, non-included side, two angles, non-included side. So we are given AAS, and we're going to prove ASA, that we can actually use ASA instead. If you know two of the angles are congruent, this is our third angles theorem. We know that actually that means that angle H and L would be congruent to each other. And now right over here, now we have ASA. By using the third angle theorem, we now have ASA. So we can actually say the triangles are congruent by ASA instead of AAS. So this is just showing us that these two things are actually equal to each other. Again, I said this earlier, but I'll reiterate. We're just going to use whichever one is easier to use for a given problem, whichever one makes more sense. Sometimes it's easier to show two angles in the non-included side. Sometimes it's easier to show two angles in the included side. It doesn't matter which one we do. They both lead to the same conclusion that the triangles are congruent. We're just going to pick one of them when we do a problem and just go with that. This is just kind of briefly explaining how they actually are equivalent to each other. Okay. Sorry. So let's do some actual proofs of this. So this should be expanding upon what we did just yesterday with actually writing down the proofs for like side angle side or side side side. So we are going to use angle side to prove that these two triangles are congruent. So angle side. I'm going to go through the whole process just like we did last time. So we are trying to prove that triangle ABC, so that's this one, is congruent to triangle EDC. Okay, so we're trying to show these two triangles are congruent. Pretty obvious here that was going to be the case, but that's fine. The only thing that we're directly given is a side pair, right? The only thing that's directly given are that these two sides here are congruent. So we're given sides. The other thing we're told is we do have some parallel lines. Parallel lines are important. So AB and DE are parallel. That is given to us. When we have parallel lines, we can use all of those different parallel line angles. So here, we actually have some alternate interior angles. Since these lines are parallel, I can also consider, I'm going to do a little bit of erasing here because I have a little bit too much on the screen. Once we have parallel lines, so AB parallel to DE, I can think about these other lines as transversals. So BD is a transversal, which means angle B and D are alternate interior angles. So angle B would actually be congruent to angle D because they are alternate interior angles. This is also true for this line over here. Sorry, this line over here, AE, could also be a transversal, and that creates some alternate interior angles here. So angle A and E are alternate interior. So both of those are congruent by alternate interior angles theorem. these are going to have to be some separate statements in my proof. I'll have to state these because I'm using the idea of parallel to get there. Once I have that all marked in there, now I should have the conditions for angle, angle, side. I have two congruent angles and then a non-included side. So that is enough for AAS. You also might have noticed in this picture, I'm actually not going to make use of it, but I do have some vertical angles that I could also use if necessary. But that's actually going to be extra because I already have angle, angle, side already done. So I won't need those at all. But I could use them if I wanted to do a different proof. So just like any proof, I'm just going to begin with my given statement. So AB is parallel to ED, and BC is congruent to DC. Those were both given. Now the order of things is not that important. We can kind of write these out whatever order we really want. Just going to put some symbols on there. This was my side, right? That's this side statement. I need to now make these angle congruent statements. So I'll go ahead and put those in next. So angle B is congruent to angle D by alternate interior angles theorem. And the same is true for angle A is congruent to angle E because of the same thing, alternate interior angles theorem. Again, that's because we have parallel lines. So you could sort of think about this as this idea is helping us say these two things. Because we have parallel lines, we know we can use alternate interior angles. These are our angle congruent statements. So now we have angle, angle, side. We've said all three pieces for an angle, angle, side proof. I didn't do it in order because the side was a given, so that actually went first in my particular proof. But if I wanted to, I could move this down to do it down there, but it doesn't matter. I'm just going to leave it where it is. So that's enough. Now we can just say our triangle congruent statement. Triangle ABC is congruent to triangle EDC. We always want to end with whatever it is, and then we used angle, angle, side, triangle congruence. Theorem. You can just write AAS. You don't have to write the whole thing, but I just was writing the whole thing out just to be a little more formal right here as we're doing this our first couple times. This was not a super long proof, similar to some of the ones we did yesterday. We were given one of the things, one of the sides, so we had to have a couple more statements in the middle to get the other two pieces of information that were necessary for us to write this proof out, and then our final triangle congruent statement. These aren't going to be really any harder than the side angle side or the side 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 proofs. Sometimes the parallel line stuff does trick people up a little bit. They have a hard time noticing the alternate interior angles, but I'll just say, make sure you're looking for those. If you're looking for alternate interior angles anytime you got parallel lines or corresponding or anything like that, you're going to find them, and it's going to be a little bit easier for you. All right, let's do one more. I'm actually going to undo this real quick. This proof could have also been done by ASA instead. If I used these vertical angles, then you can see I could have done AAS instead, or sorry, ASA instead, because right down here I have angle, side, angle, angle, side, angle. So I could have done this by angle, side, angle instead, but since it told me to do it this way, I went ahead and did it that way. All right. Next one, again, this one's not going to be too complicated. This is kind of about the hardest type of proofs that we're going to be really asking you guys to do. So let's go through the whole process here. Just checking on the time. Okay. So we are trying to prove the triangle JKL, that's this top one, is congruent to JML. All right, so that's pretty obvious. I was just verifying which two triangles we were looking at, but again, it's pretty obvious there's two triangles here, and those are the ones we're showing. It's worth looking at, though, just to make sure we know. Let's see. JL, that is this segment right here, bisects angle KLM. So angle KLM is up here. So this angle is being cut in half. These two parts are going to be equal. To make it easier, I'm going to put some numbers here. I'll call this 1 and 2. So we know that angle 1 is congruent to angle 2. That's not directly stated. That comes from this statement, from what we know about angle bisectors. So this is based on the definition of angle bisector. Since we know we have an angle bisector, we know the two pieces right here, 1 and 2, have to be equal to each other, have to be congruent. So this is going to be another statement in my proof. Okay, and then we have angle K and angle M. So that's these ones are congruent. Okay, so we have two angles. The question is now, what else do we know? What else can we figure out about this triangle? We have the one that we said over here about the angle bisector. Yeah, we got a shared side in the middle. I'm seeing that in the chat. Thank you, guys. We do have a shared side. It's that red one that I just drew, right? Right here is a shared side. So we know that is going to be congruent to itself. Shared sides are always congruent to themselves. So does that give us angle, side, angle, or does that give us angle, angle, side with that? What do you think? That gives us, we have two angles, and then we have the side that's not in between them. The in-between side would be here. So yeah, I'm seeing this is AAS. Oops. So this one is AAS. So we have kind of a plan up here. I really want to draw your attention to kind of all of the prep work we did before kind of starting to write out this proof. We got to figure out what are all the things we know, what are kind of the extra things that are going to need to be said, because anything that's not directly stated, sorry guys, anything that's not directly stated in there is going to need to be its own statement in the proof. So even though this leads us to say we have congruent angles, this right here needs to be its own statement. So that will go somewhere in my proof after the givens, right? Same with this, talking about this shared side and saying that JL is congruent to itself is going to have to be its own statement in there after the givens. All right, let's go ahead and write this one out. I'm going to go ahead and write it all. I don't know, this might be faster, it might not. So JL bisects angle KLM, given. That directly led to angle 1 being congruent to angle 2, definition of angle bisector. This is one of these times where it would be totally okay to write your givens out, one of them in the beginning and another one right afterwards, because I know these two concepts are directly connected to each other. So I want to state this right after that. It's not, I don't technically have to. I could list all my givens later and then just say the stuff that follows it after that. But I do like doing it this way, just so that it's clear what concepts really go together. Our second given was that angle K was congruent to angle M. This could just as easily go up here and be with the rest of my givens, and that would be totally fine. again, the only reason I'm doing it in the way that I did this time was just to show the connection between specific ideas so that these two things were actually just next to each other. Doesn't really matter though. Okay. So that is an angle pair here, an angle pair here, and now we need to state our shared side. So JL is a shared side. So JL is congruent to JL. Remember, shared sides, we call this the reflexive property of congruence. Or you could say it's a shared side. That would be okay too. Fine, and that was our side. So now we have everything. We have angle, angle, side. Now we can actually write out the triangle congruence statement. Triangle JKL, triangle JML, AAS. There we go. All done. Not too bad. Again, about the same length as the previous proof, right? All right. This is kind of the hardest that we're really going to be asking you to be able to try to do on our little quiz that we're going to have next week. It's going to be pretty short. Some multiple choice questions, several multiple choices. So those will be more questions. But as far as proofs, you're just going to have to do 2 of them. It will be relatively simple. All right. We're going to introduce the last thing, but we won't actually get through all of it. So we're going to introduce hypotenuse leg. So now the only time you can use the ASS property, is with a right triangle. So I already said this is not a shortcut. There's a different name for it when we're doing it with a right triangle. So right triangles have their own special theorem that we can use only for right triangles. It is called the hypotenuse leg. It seems like this one is shorter and easier because we only have to show the hypotenuse and the leg that are congruent. So only 2 things, where the other theorems and postulates had 3. But there's sort of a secret thing. We also have to show that we have a right triangle. So there's still 3 things that we need when we're trying to show hypotenuse leg congruence. And again, it only works for right triangles. So if the hypotenuse and the leg of a right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. It's that simple. Remember, the hypotenuse has to be across from the right angle. So this is our hypotenuse. And then the leg is just one of the other sides. It doesn't really matter which one. We could kind of show how this works. Essentially, it's just based on the Pythagorean theorem. If you know 2 sides of a right triangle, you can always figure out the third using the Pythagorean theorem. So technically, because we know 2 sides are congruent, we actually know that all sides are congruent. So this is actually equivalent to side, side, side congruence. Some people like to think about this as a corollary of SSS. Again, it's why it's a theorem instead of a postulate, because we can prove it by using side, side, side and the Pythagorean theorem. All right, I'm going to go and stop there. I don't want to get into any of those proofs necessarily. We got 2 minutes. Homework for this week. Remember to get the there's a quizzes assignment that was posted for this week. And let me just double check what else I posted so that I don't forget. Sorry, it's being a little slow. Oh, and also the triangle congruence worksheet. So the proofs of SSS and SAS proofs. Remember, you have to turn in number 5 from that worksheet. So that is a proof you need to do from that sheet. There's also some other problems on there, but the only one you actually have to submit for a grade is number 5. But I definitely would take a look at the other ones and make sure you can do those. That's all for today. I'll see you guys tomorrow. We'll go over a couple more proof examples and stuff. Yep. See you then.